were discussing the previous class some ways of calculating energy bands using plane waves. That is basically plane wave methods. For energy band calculation. Using simple plane waves, I also mentioned at that time that convergence to higher energy states is difficult. Convergence to 1s state is reasonable. Convergence to the lowest band, often which is not of great interest, is reasonable, but convergence to higher bands which are of interest is pretty poor. But convergence to higher bands is poor. So, a way out of this was actually suggested by Hering, and what Hering did was the following. Hering said, we will construct approximate core functions, approximate core level band states, and orthogonalize the plane waves to the core states. So, if I have a plane wave e to the ik dot r, then I can orthogonalize this to core states. Let me call them phi n comma k within bracket r, which are actually tight binding states. Okay, sigma over let me use a symbol j here, because n I shall reserve for site numbers. Sigma over n e to the ik dot rn uj r minus rn. So, what we want to do is orthogonalize e to the ik dot r to phi jk of r for all core states. How does one do it? It is very simple. It is well known that in linear algebra you can actually do this orthogonalization using a Gram-Schmidt orthogonalization procedure. The projection of the plane wave on the state phi j is simply given by the inner product of e to the power ik dot r and phi jk of r, and all you need to do is subtract this projection out from e to the power ik dot r. The plane wave chi k OPW, this is the orthogonalized plane wave, is equal to e to the power ik dot r minus sigma over j e to the power ik dot r times phi j k of r times the function phi j k of r. So, this is the Gram-Schmidt orthonormalization procedure. Now, it is easy to show that this thing chi k OPW is actually orthogonal to all the core states by actually calculating the inner product of chi k OPW with phi j k of r. So, if I just want to show that chi k OPW times phi j k of r, I want to compute. So, this is equal to e to the power I k dot r phi j k of r minus sigma over j e to the I k dot r phi j k of r times, I should have chosen a slightly different index. So, made a mistake here. So, let me take it as j prime. So, this will be j prime k of r, this times e to the I k dot r rather phi j k of r times phi j prime k of r. So, this is what we have, and we know very well that tight binding functions are orthonormal. They are orthonormal. By that we mean phi j comma k of r phi j prime comma k of r is equal to delta j j prime. So, because of that I have chi OPW k times phi j prime k of r is equal to e to the I k dot r phi j prime comma k dot k of r minus, this will be delta j j prime. So, the summation over j will only give you when j is equal to j prime. So, I get the following e to the I k dot r phi j prime comma k of r, and that of course is 0. So, you see that the Gram-Schmidt orthonormalization procedure in fact creates functions which are orthogonal to the core functions. So, now let us see how they will actually look like in real space. We can have a picture of how they look like in real space. Let me draw that here. Now, let us assume that we are having a plane wave. So, the plane wave is given by, let me draw a plane wave on the lattice. So, the plane wave will be so this is a plane wave. Okay. So, and then if I want to look at the core functions, I have the following core functions I can show you. So, let us say the other one will be slightly smaller than that, and this will be nothing, and here it will be negative. So, which means that I will have and here it will be smaller negative, and here it is even smaller negative. So, this is how the core function will look like. Now, what I can do is when I orthogonalize it, how does the plane wave look? Orthogonalized plane wave, let me plot it here. Since I am subtracting it, the first one will look a little different. So this is the negative part of negative of that, and this one will be negative of that. This one will be smaller negative. This will be, sorry, I made a slight mistake here. Let me correct it. The amplitudes are not correct. So this becomes very small and slightly bigger, and even bigger. So this is how it will look like, because the amplitude, this is the envelope function for the amplitude. So now I have the other function that is going to be negative of this one. So this will be okay, and in between spaces it will look like a plane wave. So the plane wave is going this way. So this function is going to be this way it will go. So in the region between the cores, you see it is like a plane wave, okay, and in the core it is a plane wave. In the core it is an oscillatory function, and there is a core function like either the 1s, the 2s, or whatever it is. So this is how the thing will look, and probably you can look up a book like Zeeman Principles of the Theory of Solids, where he has given these diagrams. Now having done that, what you can do is, I just want to show, like supposing I take a plane wave, let us see how it will look like. Let us take a plane wave with k equal to 0. So the plane wave with k equal to 0 is nothing but 1, okay, because k is equal to 0, e to the ik dot r is 0, so it is just 1 upon root v, which is the plane wave with k equal to 0. And let me look at the 1s function. I just want to construct a plane wave that I can use for the 2s states. So if I am looking at the 1s function, the wave function for 1s is just given by alpha cubed by pi whole thing to the power half e to the minus alpha r. So you see that there is no angular dependence, and you also see that there is no node in the wave function except at infinity. Now let us orthogonalize this. So if I want to orthogonalize this, then what I need to do is following, that is my phi, which is the 1s function with k equal to 0, is simply given by 1 upon root n sigma over n, the lattice side, u 1s r minus Rn. So this is the wave function, which is the block state. Now the integral 1 comma phi 1s 1 by square root of v is the is the inner product. That inner product I can actually calculate for r is equal to capital Rn equal to 0. Take Rn equal to 0, and the inner product is one upon root v times pre-integral factor, which is alpha cubed by pi to the power half, alpha cubed by pi to the power half, and then integral e to the minus alpha r d cubed r, and this over all space because it is a 3-dimensional integral. So what I really want to do is the following, that is, I want to calculate 1 upon root v 1 phi 1s, which is equal to 1 upon root v sigma over n u r minus, and there's a 1 upon root n, r minus rn integral, this is the 1s, and this is d cubed r. Chi OPW will be equal to 1 minus, and there is a factor of 8 here. So, this quantity will be 8 times pi by alpha cubed into 1 upon v whole raised to the power half. So, that is the this integral 1 phi comma x. This is equal to the plane wave, which is e to the I 0 dot r times phi 1 s. Okay, so now if I were to substitute this one times I have the function u1s of r, which is alpha cube by pi to the power 1 half. So, that will cancel here, and what I would get will be the following function. So, this will be 1 minus 8 e to the minus alpha r into a normalization constant which comes from n 1 upon n v to the power half. So, this is the chi OPW for k equal to 0 for 1s. Now, let us see where the node is. If it is indeed, if the chi OPW should correspond to the 2s band, because we have orthogonalized the plane wave to the 1s band. So, then it should have the node should be at the 2s band, 2s orbital, and the 2s orbital node is actually at alpha r equal to 2.07. Okay. So, alpha r equal to 2 is the, so the 2s node is at alpha r equal to 2. So, here if I were to calculate the node, I have 1 minus 8 e to the minus alpha r should be equal to 0, or alpha r should be equal to 2.07. So, you see that the orthogonalized plane wave for the 2s state has nodes at exactly almost the same value of the alpha r at which the 2s orbitals of the node. So, in that sense we note that the orthogonalized plane wave have the right characteristics, and so we can actually go ahead and use them as the basis functions. So, now if I want to use them as the basis functions, then I have to set up the Hamiltonian matrix in terms of the chi k OPWs. So, I have the chi k OPW is the states I have. I will just call it chi k, and I have to set up the Hamiltonian matrix in the chi k basis. So, here we have k plus k1, k plus k2, etc. are the OPW functions. Because of the lattice symmetry, you only have Hamiltonian matrix elements between k and wave vector, which is related to k by one of the reciprocal lattice translation vectors. Having said that, now let us see how we can get this matrix element, which is chi k h chi k prime. This is equal to 1 upon n v times integral e to the minus I k prime dot r. So, which means I am taking it as k prime and k minus h cross squared by 2m del squared plus v of r e to the I k dot r minus integral e to the minus I k prime dot r minus h cross squared by 2m del squared plus v of r times sigma over j mu kj phi kj of r d cubed r. So, this is one, and the other one will be minus integral phi e to the I k prime dot r e to the minus I k dot, this will be plus I e to the I k dot r minus h cross squared by 2m del squared plus v of r times sigma over j mu kj star phi kj star r d cubed r. And the last one would be plus sigma over j prime mu kj star mu k prime j, there is no star, times integral phi k prime j minus h cross squared by 2m del squared plus v of r phi kj of r, so there will be a star here, phi kj of r d cubed r. The star will be on not the k prime, but it will be on the k. So, this can actually be, we can notice one thing, that is h phi kj is equal to e kj phi kj, and we have phi kj, because of that phi kj phi kj prime is equal to k prime j prime is equal to delta k prime minus k comma kn km and delta jj prime. So, that is the orthogonality relationship that we have for the phi case, because they are eigenstates of the Hamiltonian with different eigenvalues. They correspond to different eigenstates or different Courte states. So, with this what we can actually simplify is the following. I have chi k h chi k prime is equal to k squared delta k k prime plus v k minus k prime, okay, and this will be delta k minus k prime comma km and then I will have minus of sigma over j mu k prime j star mu kj e kj, and in fact what we will get is there is no prime here, because only when both of them are the same you will have, because of the delta k k prime that you have. Now, we see that this is the Hamiltonian matrix, and once we have the Hamiltonian matrix, then we can obtain the solutions. So, we can obtain the eigenvalues using diagonalization techniques. Well, there are certain problems with the OPW method. First of all, the Courte states are not exact eigenstates to the Hamiltonian, crystal Hamiltonian. Okay, problems with OPW method are the following. One, core states are not true eigenstates of the crystal Hamiltonian. So, if they are not the eigenstates of the crystal Hamiltonian, then what is the error that we are going to introduce? So, we can estimate the error due to orthogonalization problems. Error due to orthogonalization to approximate functions as follows. So, what we will do is the following. Let us assume that I am going to be dealing with the valence state, which is actually, I call it psi prime k comma 0. So, the notation is 0 means valence state and prime implies approximate state. So, because whenever you do a diagonalization of the OPW, you only get approximate states. So, it is an approximate state. So, now let us assume that we know what are the exact states. If the exact eigenstates of the core are psi k s. Notice I have not put a prime there because I am saying that they are exact. So, only the approximate ones I am going to put a prime on. So, now we can expand psi prime k comma the valence state 0 as sigma over s psi k s psi prime k comma 0 times psi k s. So, this is because psi k s form a complete set. Form a complete set. So, you can expand any function, and in particular you can expand psi prime k 0. Now, what is E prime k 0 given by? E prime k 0, which is the approximate valence state energy, is given by psi prime k 0 h psi prime k 0, and that I can substitute for psi prime, and I can write it as sigma over s modulus psi k s, which are the exact eigenstates of the core states or whatever the basis states, times psi prime k comma 0 squared into psi k s h psi k s prime. And this prime should be, so I have a double summation, so I must have sigma over s s prime, or this will reduce to sigma over s modulus psi k s psi prime k comma 0 squared times E k s. Now, we are assuming the orthogonality of the eigenstates of the Hamiltonian. So, I have a psi k s prime inner product is delta s s prime. Now, what we can do is we can subtract, to get the error we have to subtract this quantity E prime k0 from the exact energy which is Ek0. So, if I have Ek0 is the exact energy, this minus E prime k0 is equal to sigma over S psi ks psi prime k0 squared Ek0 minus Eks. So, now what we are going to be doing is the following, that is, try to get a bound on this error. So, we know that for all core states say up to S equal to some P, the energy Eks is always going to be less than Ek0. So, because of that, the positive error will only come when you sum over the core states. You do not get the positive error. If you go to higher states when S is greater than P, then this quantity is going to be negative and it will start reducing the error. So, Ek0 minus E prime k0, we can put a bound on that, which is it has to be less than sigma over S is equal to 1 to P psi ks psi prime k0 squared times Ek0 minus Eks. So, notice that the summation is going to stop at P, it is only summation over all the states which are going up to the core levels. So, instead of S I can actually put J if I want, but it is one and the same. Now, let us see what we can do from here. So, we can express the exact eigenfunction psi kj in as two parts. So, now let me look at say psi ks, okay, can be expressed as a sum of projection of psi k s on phi k s, projection of phi k s on psi k s, where phi k s is the approximate state, times phi k s. And a projection of psi k s on psi k prime 0, psi k 0 prime, sorry, times psi k prime 0. This is quite alright because of the following reason. Okay, let me justify it. See, the problem with psi prime k0 is because it has got a part of the core function inside it. So, I have to get the core function that is there in psi prime k0, and then that is a correction that is added to phi ks, and the part that phi ks is going to contribute is the projection of phi ks onto psi kj. So, what I am trying to say is that psi ks is equal to projection of phi ks on psi ks times phi ks plus what is in the valence state because of the incorrect orthogonalization to the incorrect function. So, that is given by psi rather phi ks psi prime k0 times psi prime k0. So, basically I have tried to express it as a combination of the true function plus the part of the function that is there, part of the phi ks the psi ks, which is the true psi ks, is partly in the core state and partly in the valence state. So, the part in the core state is given by this quantity and the part in the valence state is given by that quantity. So, now what happens? We can see, we can use the Bessel's inequality, which says that psi ks psi ks prime the squared, rather psi ks squared. So, okay, there is no prime here. This is equal to 1. So, we are trying to get the norm of see, we want to see how close the norm of this part, the norm of this part is going to approximate to the norm of this one. So, this is the norm of psi ks is 1 and that will be always less than or equal to the norms of the following, that is modulus phi ks psi ks squared plus modulus phi ks psi prime k 0 squared. So, this is known as the Bessel's inequality. When the basis set is not complete, okay, then the norm of the function that you are trying to expand is going to be greater than or equal to the norm of the expanded function. Okay. So, this would mean the following. So, I can now have another inequality now. Now, what I need to do is substitute this quantity. So, what I will do is 1 minus phi ks psi ks squared is less than or equal to phi ks psi prime k 0 squared. Now, let us see, we will go back here and then we see that we have an expression for psi ks psi prime k 0 the whole squared. Now, I can substitute for this quantity as from the expression that I have just derived, and if I did that, I will get the error E k 0 minus E prime k 0 is less than or equal to sigma over s 1 minus phi ks psi ks squared times E k 0 minus E k j. So, we have got an expression for the error that you can get because of orthogonalization of the phi ks to the wrong core functions, and this is just an estimate, and this actually you can get the details of the calculations from Callaway's book on energy band theory. I think I will stop at this point. This is all that I wanted to say about the orthogonalized plane wave methods, and in the next lecture I will try to introduce the concept of pseudo potentials and how it comes about from the concept of orthogonalized plane waves. So, thank you.